we're going to, in this video, we are going to look at dynamic tables in connection to hash tables, and then we're going to analyze using amortized analysis, in particular using energy function or potential functions to analyze the complexity of a sequence of AND operations on dynamic tables. Okay, so dynamic tables, a table is dynamic is because that the size of the table can be expanded when it is needed, and the size of a table can also be contracted when the actual space is no longer needed. So this is a better way to manage the main memory of a computer. Okay. Okay, so first let's look at hash tables. A hash table T is a data structure consisting of two things, right? So first of all, you must have an array. So let's say we have an array. Okay, so, and let's say we have set up the size to be n for this array. So let me change the color here to blue. Okay, so that's the first thing. And then we also have a hash function, h. Okay, so that will, so this h, let me put it here. So this h will map a universe. So let's say this would be the values that for keys that you want to, right? So you have value k, and then you have a key value k, and you have the actual items under that k. So you could have lots of these, right? So you could have, let's say this k1, k2, 1, v2. So you got lots of these. So you want to store these items in this array, and you want to have random access. Okay, so so these k's, this ki is not in the range of 1 to n. So it could also be, so it could be from a different universe. So what you want is to hash these values so that it's between so that this value is in the range from 1 to n. And moreover, we want we want this h to be to map these key values, these keys to this range as even as possible. Okay, so that's what this hash function is. Okay, so we want to change our indexes from 0 to n minus 1, because that's more convenient for modular operation. So it's still the size of n. So what we want here is this. Okay. All right. So here we got an assumption that, so we have an assumption that computing h of x for a given key x is a constant time. Okay, so it should be straightforward to calculate when you are given x what h of x is. regardless of X. So then a hash table supports two operations, insertion and lookup. Okay, so what you want is you have a pair KV, then you want to insert this PK with, or this pair, okay, with value V into table at location H of K. Okay, so in other words, this is what we want. And then when you do a lookup, so you want to retrieve the value of a given key K. So that's a lookup process. So returns the value associated with key K. And of course, hash table should also support deletion. So when an item is no longer needed, you provide a key, then you can remove the key from this table. But right now we're just looking at insertion and table lookup. Okay, so when you have when you have more items, let's say you have greater than n many items to be placed in this array, then obviously we know that collisions will occur. So which means that you could have h of k1, which is equal to h of k2, where k1 is not equal to k2. So this is a collision. Okay. So then how to handle collisions? One way, the easiest way is to show it up, to say failing. But the common way to do this is to maintain a linked list so that we can just link every pairs with the with the same hash value of key, with keys that have the same hash value together. So that will just look like this. So you have 0 and -1. Let's say this particular one is called h of k1. Then we're not going to directly place k1v1 into this array. Instead, we maintain a linked list. So we're going to put k1 v1, and then you have k2 v2. Okay. And so you maintain a linked list. Let's say this k2 v2 comes first, and then you can always do an insertion at one end. So that means that insertion is a constant time operation. So this is insertion, and then when you do a lookup, so you first get to the head of this chain for any k, and then you search for an item in that linked list, and under the assumption that h evenly distributes its hash values, then the average length of each linked list will be called, so this is T, will be denoted by a load factor. So this is alpha of T, which is the total number of insertions so far divided by n. Okay, so that is a load factor. So so again, the assumption to make this happen is that H evenly distributes the hash values. Okay, so that is a popular way to handle collisions. The other way is to use open addressing. What it means here is that, let's say I have a table, and then let's say this is K, so then I also have K1 comes in, and we already have an item here. Let's see, KV, it's already there. But then for a new item, K1, V1, we compute H of K1, and that is equal to H of K. So then, but this is already taken. So what I do here is that I'm going to use some kind of a mechanism to find so jump to a different location and see whether that is available. If that is not available, I'm going to jump again. If that, so we following certain functions, which we're going to talk about. If that is not available, maybe then you want to jump to a different location. So this time, maybe, then this is available, then you can put K1, V1 in it. Okay, so that is the idea. All right. So open addressing. So every bucket holds one element. Instead of holds a pointer to a linked list, a sequence of locations is used to find an empty slot for insertion or the correct entry look. The entry is to be looked for. Okay, so that following some kind of mechanism, which we're going to talk about. So then the sequence that jumping, so it's called a probe sequence because we're just probing to see whether a location that we jump to is available. So that's why it is called a probe sequence. A bootstrap probe sequence. To bootstrap probe sequences modified, then we need to modify hash functions to include a probe number. Okay, so the probe number is the number of insertion collisions so far. Okay, so now let's look at these two operations, insert and lookup. So let's say we want to insert this pair or this key, this pair KV, okay, under key K in the first shell. So we compute this, and this is the probe number. So that is empty. Okay, then we probe a few times, so that is empty. So then we found that that's empty. So the runtime for insertion is proportional to the length of the probe sequence because you first find, right? So let me do this again. So you first find this, and that is already taken, and then you probe the other one, and if that is still not available, you probe under certain mechanism, and then you probe, okay, at this time, so this I is equal to 3, so the number of times you probe, then you found an empty space, then you place all your items in it. Okay, so that's easy to see that the runtime for this insertion, the runtime for insertion is proportional to the length of the probe sequence. Okay, so of course we know that this is also related to the load factor. So how many items that you have already inserted into this hash table T. And if at the beginning a lot of spaces are vacant, and this is easy to find, it's easy to find an empty space, okay, with a very small number of probing. then you can find an empty space. If the load factor is high, that means a lot of spaces are taken, then you may need a longer probe sequence to find one. Okay. And for table lookup, so let's say we want to search again. So you repeat the same process of the insertion. So, right, so you first compute the hash value of K and go in there and then see, oh, this is not the one I'm looking for. Then you, under the same mechanism, you go to the same sequence of probes, same probe sequence until you find your item. So that means that the runtime of doing so is also proportional to the number of probes that you start, number of probes that you find the items you have. Okay, so this is pretty straightforward. The idea is straightforward. And then, of course, how do I come up with such H taken and with a number of probes taken? Okay, now let's look at probing strategies. 3 common probing strategies can be used for open addressing with an initial probe number, I being equal to 0. So this is a function. So basically we just define a function. So let's say your h prime is the original hash function, which only takes a key value. Now I want a function that takes the key value K and the number of probes I as input. So that's what we are going to do. So we simply add I to h prime of K and take the modular n. Okay, so this is very, straightforward. Or, so this is a linear function. So linear function, almost the same distance. So it's almost same, it's slightly different because this I is changed. So maybe we want to make it a little bit more sort of, a little bit more a different function that may be easier to get to find an empty spot. So this is called a quadratic hash. So you use the original, and now it takes I as input. So we plus C1I plus C2I square, and then still take the modular n, and C1 and C2 here are positive constants. Say 1, right? So you could simply h prime k plus I square, and take the modular n, and this would be your k h of k comma I. All right, and we can also use double hashing. Okay, so given 2 different base hash functions, so one we call it h1 and h2. And then what we want to do is just add this one up, h1 of k plus I times h2 of k, and take the modular n approach. So this is also fairly common to use. And as a matter of fact, you could probably looking at this one, which of course this is equal to I, and this is 1 plus I. All right, so it doesn't have a k in it, but sort of like, so I have this function, maybe you replace this with a different hash function. Okay, so this is probing mechanisms. Okay, so probing mechanisms. Okay, so we haven't talked about deletion for hash tables, so we just insert items. But at some point, if you don't use linked lists, then at some point your table will be full. So what to do then, of course, when the table is full, I can enlarge that table, I can expand it. So this is a full, let's say I'm gonna double its size. Okay, so then of course you want to redo your hashing. Okay, so we can double a table or halve a table when needed. So when the number of insertions m into the table is the same as the table size, so that means the load factor is equal to 1, then we can double the size of the table. So to double the size of a hash table, we first allocate a new table. Okay, so this is an old table that's full. So this is full. Then I'm going to create another table which double the size of t. So let's call this t prime. Okay, but then all the items here will need to be copy over under a new hash values. Okay, but then so if this is n, because each hash takes a constant time, each hashing takes a constant time. So moving this over will still takes a constant times n to move this over, and then you can then it may not be all in here, right? So under the hashing, maybe they evenly spread out. So this is occupied and some others not. Then of course you can put more items in it under a hash value. Okay, so that's doubling. Next, we're gonna see how do we analyze, okay, the cost of the n operations. You have insertion, and suppose you also have a deletion for certain items in this table, in a dynamic table, and you can delete them when you no longer need it. So that means that a table can be doubled and can also be halved. Okay, so we didn't look at a halving here. Okay, so halving just means this. When the table is quite empty, so the load factor is small. Let's say this is my t, and alpha t is small. Let's say because you don't want to say if it's 1/2 and then 1/2, because after that, if it's about 1/2, you cut the table size, you shrink the table size by 1/2 of the original size, then maybe after that, the insertion will expand this table again almost immediately, right? Or a few steps, a few insertion after. So you don't want that to happen. So maybe the better way to do that is when the table is 1/4, okay, the load factor is about 1/4, then you have the table size. So that means now, if that is the case, I'm going to create a table and do a rehashing. So maybe there's some items here, and then you're gonna do a rehashing. You have still about half of the space in this new table unoccupied. So which means that you can do a few insertion before you have to expand it again. Okay, so that's table halving. So we're interested in, let's say I have a sequence of n insertion and deletion, and I want to know on average the cost for each operation. Okay, so we're going to use a potential function. So we want to figure out the cost of a sequence of m operations starting from a empty table, okay? Because by dynamic table, because we can start from an empty table, okay? So there isn't anything occupied. You declare a space, there's nothing in it, okay? So insertion and deletion form potential energy for the next possible expansion or contraction. So again, we know that the energy is really, energy function really measures the current state of that memory or that data structures. Normally, we just look at how many items in that data structure, or a load factor. You can use a load factor as well. So the load factor, we can use 1/2. We can use a load factor of 1/2. So that means that when the table is half full, then we may need a double or contract. Okay, but nevertheless, we're gonna use that as a midpoint of measuring defining an energy function. So this is phi of t is as follows. Okay, so when the load factor is at least 1/2, greater than or equal to 1/2, at least half full. So this load factor, let's write it as alpha t, which is L of n. So when this is greater than or equal to 1/2, it really means that 2L is greater than or equal to n. So we look at the difference to be the energy, to measure the energy in that case. So this is then 2L minus n. Otherwise, if the load factor is less than 1/2, so it means that it means that L is less than, okay? So it means, in this case, L is less than n over 2. So we want the difference. So that's n over 2 minus L to be the energy. So we don't want a negative energy. So this is a positive energy, non-negative energy. Okay. So that's a energy function we use to carry out amortized analysis for a sequence of n insertion and deletion to a dynamic table starting from an empty table. Okay, so now first we need to check that such a function, such a potential function is legitimate. Okay, so we want to check. So legitimate means that we want a table So at the end of the table, or at any single moment, that table, so maybe we can say Ti will be at ice after the table after the ice operation, because it would have expansion and contraction somewhere before that or at that time, right? So we want that the value of this is greater than or equal to 0. And initial energy when this table is empty is just 0. So this is what we want to have. Now let's see. For this particular definition earlier, so remember that definition is, okay, if load factor L of n is greater than or equal to 1/2, that's 2L minus n. If L of n is less than 1/2, is n over 2 minus L. Okay, so if L is empty at the beginning, so we know that at the beginning there isn't anything, and so we don't have a table, right? So so that means n is also equal to 0. So that means that if T is empty, of course at that time the L and N are both 0. So of course there isn't any energy there. Okay, so if alpha T is 1/2, then we know that, so exactly, right? So this is exactly 1/2. Then 2L is equal to n. So this is also 0. Okay, and then when alpha T is 1, then we get 0. So I'm sorry, we get n. So that means that with potential n, so the reason we have this is because when it's full, we got to expand it. Okay, so that means that when you expand it, you will get n extra space, right? So get n extra space that you can use. And if alpha T is equal to 1 over 4, we know that we're going to shrink, we're going to shrink the table. Okay, so when shrinking happens, so we know that L over n, well, this is a load factor is 1/2. When it shrinks, you get rid of, so the new table, the size of the new table is n over 2. Okay, so then L is equal to n over 4. So that you still have about, so this is the old now. This is the old, this is the new. Sorry, let me put it this way here. Now it's a dynamics thing, so let me write it better. Okay, so let's say, for the sake of showing this now, then let's say this is a 1/4, all the items are here. In reality, they spread out, right? In reality, they spread out, but just for the sake of demonstration. Okay, so then I cut it into half. So get rid of it. So that means I still have about 1/4 of space. I'm sorry, this is 1/4 of the original, but then the new, so this size is halved. So that means that I have about half of this in the new table that's taken. So about half is not taken, right? So that's that's what it is. And then you look at the energy. So in this case, L is equal to 1/4, and then n over 2 minus 1/4 is equal to so let's change it to, okay, so that means 2L is equal to n over 2. So then we have n over 2, that's 2L, 2L minus L is L, right? So L is equal to 4n, 1/4 of n, but after halving, it's equal to 1/2 of the size of the new table, okay, after shrinking, after halving. So now we want to check that the potential is non-negative for the following reasons. Okay, so let's focus on this. Let me erase this. Erase that. And just let's focus on this potential function. Okay, so because when L over n is greater than equal to half, so this is always greater than or equal to 0. And when this happens, this is always strictly greater than 0. So we know that this is legit for any situations, because for any moment, right, on your dynamic table, because it's never negative. Okay, so that's why it is a legitimate potential function. So now I have a potential function that I can use. Then now I can carry out amortized analysis for insertion and deletion. So this will be a case study, because we need to look at all the cases. So we're gonna take a look at this one by one, these cases one by one. So we start with an empty table. So at that time, the energy, so we call it T0, the energy, we know that there isn't anything, and we just assume that at that time the load factor is 1. Okay, because when the load factor is 1, alpha of T is 0. Okay, so we saw that earlier. Okay. Well, because n is 0 anyway. So that's a special case. So now the interesting case here is that suppose that the i's operation is insert. Could be delete, right? So then under this insertion, then we're going to look at the current situation of the dynamic table, or we can also say the current state of the dynamic table. So suppose that before insertion, the load factor of Ti minus 1, right? So this is so you start from T0, And then the next, after insertion, you get T1. And the next one, maybe insertion deletion, you get T2. Okay, and then you get the previous one is Ti minus 1. And then this is a Ti. So say this is an insertion. Okay, so then we have to look at its earlier one. So let's look at the load factor. So if the load factor of Ti minus 1 before this i's insertion, before this i's operation, which is insertion, is less than 1/2. And after the insertion, it is still less than 1/2. That means that no expansions occurred. No expansion and no contraction, right? So that would be then pretty straightforward. So what we're going to do here is that the amortized cost Ci hat is the actual cost. And for this actual cost, it's just one. You just insertion, right? So it's an insertion. Okay, so then we look at the potential value. So both of these are less than 1/2. So then this is equal. So that's phi of Ti. And this is phi of Ti minus 1. And of course, n, in this case, Ni is equal to Ni. M sub I is equal to N sub I minus 1 because there is no expansion, no contraction. And L sub I minus 1 plus 1 after one insertion then is equal to L sub I. Okay, so then we just replace it. We get, okay, so Li is equal to this. And Ni is the same, so we get down to this. So after that, we see that this is canceled, and this is canceled. And 1, we have a minus here. 1 minus 1 is 0. So the amortized cost for this case is just 0. Okay. So this is probably is the easiest case. Okay, so now let's look at case number 2. So the case number 2 is that, so the load factor before this i's operation, that's insertion, is less than 1/2. But after this insertion, it becomes greater than or equal to 1/2. Now, remember this 1/2 is a transition point of different values made by this potential function. Okay, so, and suppose that's the case, and suppose that the table does not expand. Okay, so the table, because when this is equal to 1, then you got to expand the table, right? So when this load factor of this insertion becomes 1, then you got to expand. So that means that alpha of Ti is not equal to 1. So this is still less than 1. That means that table does not expand. So still less than 1. So then we compute the amortized cost Ci hat, which is equal to Ci plus phi of Ti minus phi of Ti minus 1. So then we plug in the definition. So this is Ti, alpha of Ti minus 1 is less than 1/2. We plug this one in. And it's greater than or equal to 1/2. Sorry, this is greater than or equal to 1/2. We'll plug this in. This is less than 1/2. We plug that in. Okay, so once again, let me write this down here. T is equal to 2L minus N if L or alpha of T. Okay, so if L over N is greater than 1/2, otherwise, we're going to do N over 2 minus L. So less than 1/2, we're going to use this for that. And greater than or equal to 1/2, we're going to use this for that. Okay, so in this case, we still have L sub I minus 1 plus 1 is equal to Li, and we still have Ni minus 1 that's equal to Ni because the table is not, the size of the table is not changed. So then we plug that in for Li, and for N sub I, we plug that one in. So after this calculation, so we can see this, you have a negative N sub I minus 1, you have a negative N sub I minus 1 over 2, so you get a negative 3 over 2 times N sub I minus 1, and then you look at Li minus 1, you got a positive 2 times positive. So this minus minus becomes positive, so you get 3L sub I minus 1. Okay, so then I can change, right, for this Li minus 1, I can, so this is equal to Li minus 1 over N I minus 1 times I minus 1. So this is alpha Ti minus 1 times N sub I minus 1. So we know that this is less than 1/2. Okay. So that means that is less than 3 over 2 and I minus 1. And then this got canceled, so we got 3. So this is the amortized cost analysis for this case. Okay, slightly more involved, but it's not too bad at all. So there isn't any dynamic situation. The table size has not changed in this case. So let's look at what happened if the size of the table is changed. Still, we have one more case. So I forgot. We still have one more case that the table size doesn't change. So that's case number 3. So before insertion, the load factor is greater than or equal to 1/2. And after the insertion, the load factor obviously is greater than or equal to 1/2, but it's still less than 1. Okay, so that means that the table doesn't expand. And obviously no shrinking either, not shrink either. So then the amortized cost is equal to this, and both time now, so both load factors greater than or equal to 1/2. So you use this part of the, from the energy, so potential function, you use this, and the same thing still happens. We still have L sub I minus 1 plus 1 because it's insertion. That's Li. If it's a deletion, you got the minus 1, that becomes Li, right? And then the size of the table is not changing, so this is equal to this. Okay, so then we plug that in. So then we got this, and this canceled, and we got 2 times 1 left. So that's 3, and that gets canceled because this is negative, negative becomes positive. This is negative here. So that's case. So now next case is that before insertion, the load factor is greater than or equal to 1/2, and after insertion, the load factor becomes 1. So that means now they're going to expand we need to expand this table. So that means that n sub I now is equal to 2 times n sub I minus 1. And Li is, because after that is 4, so that means Li is equal to n sub I minus 1. Because you got a new Ni here. And then Ci is equal to Li. So that is the total number of insertion. Okay, that's the cost. Because, so actually we probably want to say that because we are going to use hashing. So hashing, again, we need to take a big O of, each hashing is a big O of 1, but you have this many hashing, and also you got to copy over. So maybe Ci, we can write it as a big O of Li. Okay. All right. But if we just, for the sake of demonstration, let's just say we copy, we just need to copy for the dynamic table. We just need to copy Li stuff over. So the cost is just L sub I. Okay, so just, oops, just remove this. That's easiest to see how this dynamic table is, this potential function for this dynamic table would look like. So now this is, we have this. Okay, so Ci is equal to Li, and potential function for Ti is, well, once again, let's write that one down here, which is 2L minus N if the load factor is greater than or equal to 1/2. Otherwise, it's this. But in our case, this is not happen. So that both of these, we're going to use this part of the formula so that we have this. Okay, so then this Li is equal to n sub L minus 1. Okay, that is the size of the table before expanding. And because this is full, so that means that is equal to n sub I minus 1, and Ni has been expanded. So that is equal to 2 times n sub I minus 1. That's what we have here. Okay, so we also have that n sub I minus 1 is equal to Li, and Li is equal to L sub I minus 1 plus 1. So you put things together, then we can see these two canceled. And so we get one copy. Okay, so this 2 times this minus the 1 copy left, and then minus 1 plus 1, the plus 1. Okay, so we know that Li is equal to Li minus 1 plus 1. So Li minus Li minus 1, Li minus L sub I minus 1, then is equal to 1. 1 plus 1 is equal to 2. So that's what we get on this case. So as you see, that amortized cost is still constant here, even though you have expand, you have expanded the table, you have doubled the table size. And because of the doubling, you need to do a linear operations of copying existing elements over from the old table to the new. But under this amortized analysis, we know it is still constant. Okay. Now let's look at deletion. So let's say, for insertion, we have looked at all possible cases. Then for deletion, we have also need to look at all possible cases. Okay, so we're going to look at them one case at a time. So let's say now it's a deletion. The i's operation is a deletion. Okay, so let's just write that one down. So that the i's operation is a deletion. So that means that L sub I is equal to L sub I minus 1 minus 1. So it's a deletion. So this is always hold. The only thing that we need to worry about is the relationship between Ni and Ni sub minus 1. If the table is not, the size of the table is not halved, is not reduced, then they are the same. Otherwise, right? So two cases. So either, so m's I is equal to this is not, because of deletion, you can only halve or reduce the size. So this is not reduced. Size not reduced, or reduce the size, that means that it's equal to reduced by 1/2, right? So either this or this. So we need to determine which case it would be. So the first case we're going to look at is that, okay, so this halving did not occur. It's not the table is not contracted. The load factor is less than 1/2, and the table is not contracted. So in this case, that means that after deletion, the load factor is still less than 1/2. So that means that we use the second part of the energy function and plugs these relations in, right? So this Ni in this case, no shrinking. So Ni is equal to N sub I minus 1. And Li here is equal to this. So we plug that in. So then you see this is canceled. That's canceled. And this 1 and 1, negative, negative becomes positive. So this is constant 2. Okay, case 2. So suppose that before deletion, alpha t sub I minus 1 is less than 1/2, and after deletion, it becomes 1/4. Okay, it could happen, right? So then contractions occurred. Okay, so that means now this time you halved the size of the table. So that means that N sub I in the new table is 1/2 of the size of the old table. Okay, again, we still have this. Okay, so then the load, let's say the load factor, because this is less than 1/2, you to delete 1, the load factor is still less than 1/2. So we are using the second part of the energy function. So we plug those relations in. So you can see here, this is still equal to So we get down to this. So 4 and 4 cancel, and Li is, so negative Li is negative L sub I minus 1 plus 1, so we got 2. So this is a constant time. Okay, so case number 3. Before this deletion, this load factor is greater than or equal to 1/2, and after the deletion, the load factor is less than 1/2 and no contraction. So that means that Ni is equal to Ni minus 1. Again, L sub I minus 1 minus 1 is equal to L sub I. So for the new one, we're going to use the second part of the energy function. And for the old, for the previous one, Ti minus 1, we use the first part of the energy function, that is this. Okay, so plug in these relations, then we can see here this, you can have so this is minus, and minus becomes positive, you get this. And this is a negative. This is also negative, you get negative 3 times that, right? And then this 1 plus 1 becomes 2. So this 1 plus 1 becomes 2. Okay, so that means now I got this, are using the same old trick. So this Li minus 1 is equal to L sub I minus 1 over N sub I minus 1 times. And this is alpha because we want to use this. Okay, so that's Ti minus 1. So this is greater than or equal to 1/2, and the negative will be, so it's a negative then, it's less than or equal to 1/2. So there we have 2, we get down to this. So this cancels, we get 2. So this is a constant, right? Still constant. Then we have our last case. Before deletion, load factor is greater than 1/2, greater than or equal to 1/2. After deletion is still greater than or equal to 1/2, so no contraction. So in this case, we use the first part of the energy functions, that is this. So again, we have this. And we have this. So plug these relations in. We have that. So then this canceled. That's canceled because negative becomes positive. And we have a negative 1 here. Right. So minus 1. So 2 times that. So then we get minus 1. Okay, so there's still a constant. So that's the runtime of sequence of N insertion deletion on T is linear. Just add them up. It's still linear. All right, so that is the end of this topic on dynamic table.